This is the lecture for lesson 27. This section starts with exponential functions where we will identify them, evaluate them, and then find the equation given an initial value and a point. The following are examples of an exponential function. What's going to happen is we're going to have a number as the base, and the exponent is going to be the x. So this first one here, b to the x, could be like 2 to the x power. The next one is two numbers multiplied, so maybe that's 2 times 3 to the x power. The next one, like 2 times 3 to the 3x. So again, we still have that base is the number, the exponent is the power, e to the x because e is a number, e to the kx, so maybe that's e to the 5x. The other things that have to happen, so 1 is the base, is the number, 2, the x is in the exponent, and 3, the base has to be a positive number. Base is positive. So taking a look at number 1, it has 4 functions listed, and we need to determine are they exponential functions. So the first thing is the base a number? Well, in this first one, no, the base is x. So this is no, because the base is x. When I look at the next one, negative 3 to the x. So the base is a number. The power is the x, but the problem is the base is negative. So no, because the base is negative. That breaks the third rule. Looking at this next one here, we have 1/2 to the x power. So the base is a number, 1/2. The power is x, and the base is positive. So yes, we have one. So C is our yes. And if you look at D here, negative x to the x. So there's lots of things wrong here. The base is not a number, and it's also negative. So this is no. Base, not a number. So what makes a exponential function? The most general form we're going to follow is f of x equals a times b to the x. And we're going to represent a is the initial value, and b is going to be the rate at which this function is changing, or that initial value is changing. Are we doubling every time? Are we halving it every time? Are we tripling it every time? The next thing we're going to do is evaluate these functions. So if we have the function f of x equals 2 plus 5 to the x minus 1, find f of 4. So all they're wanting us to do is plug in 4 for x. So 2 plus 5 to the 4 minus 1. Well, that is 2 plus 5. 4 minus 1 is to the third power. So we need to figure out what 5 to the third power. That's 5 times 5 times 5. And that is 125. So 2 plus 125 is a final answer of 127. Looking at 4, the exponential function f of x equals 40 times the quantity 1.83 to the x models the average amount spent in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 3 hours? So 40 times 1.83, and we're going to put to the third power there. Now, the only way to do this is, in fact, with a scientific calculator. So I will show on the slide here how you would enter that into Desmos and get the correct answer. So that should give you 245.14. We want to go to the nearest dollar, so that's going to be $245. you can see here that I used the Desmos calculator. I did 40 open parentheses, 1.83 close parentheses, and raised it to the third power, and I did get the correct answer. So the next thing we're going to do is write the exponential model if we're given the initial value and another point. If one of the data points is in the form 0, a, then a is considered the initial value. And then using a, we can then substitute the second point into the original equation, f of x equals a times b to the x power. We'll solve for b and then rewrite the initial equation in the correct form. So we want to find the exponential function going through 0, 2, and 432. So 0, 2, that means a is 2. So we can start with writing f of x equals 2 times b to the x power. Next, we're going to plug in our x and our f of x. So f of x is 32 equals 2 times, we have to solve for b, and the power is 4. So we're going to divide all by 2. That gives me 16 equals b to the 4th. So what that's asking me is what number to the 4th power gives me 16? The other thing you can do, if you don't know that, is because this is the 4th power, we're going to take the 4th root of 16. So what you need to do in your calculator is find the n root button, and depending on your calculator, I can help you in class. There's a few different ways you may do it. You may click this and then type in the number. You may have to put the number first, so 4, and then do the n root and then type in 16. So you can play around with it for a little bit. You should get the answer of 2. The 4th root of 16 is 2 because 2 times 2 is 4, times 2 is 8, times 2 is 16. So that means our final equation is 2 times 2 to the x power. And we'll do the same thing with number 6. Find the equation for the exponential function passing through the points 0, 5 and 2, 45. So 0, 5 tells me a is 5. So I'm going to start with my function equals 5 times b to the x power. Now I'm going to plug in x and f of x. So 45 equals 5 times something squared. So if we divide by 5 on both sides, 9 equals b squared. And this one you guys should know. I can square root and get 3 equals b. So the final function here is a is 5, so 5 times b is 3 to the x power. The next section talks about working with the base e. So e is a mathematical number. It is in all of our scientific calculators. And all they want us to do is just, can you find it? Can we raise it to a few powers? So what we're going to do is we're going to locate on our calculator e and then raise it to a power. So this one wants me to do e to the 2.3. I will again show you a Desmos slide just to show you how you would do that. You should get 9.97418. We're going to 5 decimal places, so 5 numbers after the decimal. If we want to do e to the negative 0.75, again, you're going to find your little e button, and then you're going to raise it to a power, and then type in that power, negative 0.75. And this one should give you 0.47237. Number 3, you are thinking of putting away your money and are looking at 2 different banks with the same interest rate. Bank 1 does continuous compounding and Bank 2 does monthly compounding. without doing any calculations, because you don't know how to do that yet, determine which bank would yield more money for you in the long run if you were to invest with them. So we're putting the same amount of money away, same amount of interest. Do you think you want interest calculated continuously or only one time a month? Well, one time a month means you're going to go that entire month with no gain. So then they'll calculate your interest at the end of the month, put it in, and then do that again at the end of the month and put it in. If I'm doing continuous interest, I'm earning interest on that interest all the time. So that's going to make my money grow faster. So the continuous is going to provide more interest faster. So here you can see my Desmos screenshot. I did type an E just to show you what it represents. And then for all these other ones, there's two options to do this. So you can type E, and then I hit Shift 6, that's this little caret button, and that raises it up to a power so that I can then type 2.3. Your other option is to type E, then click this button here, A to the B power. That means you can raise it to any power you want. It's going to put it up there, and then you just type negative 0.75 equals, and then it's going to give it to you. If you're working with a handheld calculator, if you want me to help you find any of those functions or those buttons, just bring it in class and I will help you find that. The last part of the section is going to be looking at their graphs. So we'll look a little bit at domain and range. We will graph them in their original form, graph them using transformations, as well as create the equation from the graph. So on this slide, you can see that we technically have two different types of exponential functions, one of which is called a growth function and one of which is called a decay function. The growth function is the one on the left here, and that's when your b, or your base, is greater than 1. We're doubling, we're tripling, it's a number larger than 1. If your number on your base is between 0 and 1, it means your value is going to be decreasing. Maybe it's half, maybe it's a fifth, 2/3. Those values are going to decrease the amount of a substance that you have. We will always have these points here on the initial functions. We can also talk about reflections. So how would you see a reflection across the x-axis? Well, across the x-axis, you're going to go from a positive to a negative here. So the opposite of 2 to the x. And reflection about the y-axis is going to change the x values here from positive to negative. So instead of 2 to the x, we have 2 to the negative x. Some other properties here. If it's in this form, a times b to the x, or just b to the x, your domain is going to work for every real number, negative infinity to infinity. The range is only positive numbers. That means if we have the positive form, we're going to have all positive numbers. So b to the x, they're all positives. The range is from 0 to infinity. I cannot include 0. If you have the opposite of b to the x, that's going to be our one that's below the axis here, and then it's going to have all the values negative infinity to 0. If we throw in some constants here, we shift the function, just like we talked about transformations back in module 3. So we can have b to the x plus c and then plus d. So what does it do? Well, it shifts vertically d units. So this outside here is the vertical shift. And then c is the horizontal shift in the opposite direction of the sign. So if it's plus c, we're moving left that amount. If it's minus c, we're moving right that amount. The y-intercept now becomes b to the c plus d. Our horizontal asymptote is now at this value, so our range now is limited by that value, so we cannot cross that value. The domain is still going to be negative infinity to infinity. First graph we're going to graph is 2 to the x power. So one thing you can do is you can know that anything in the original form cannot cross this axis. So I'm going to draw that little dashed line because I know I can't cross that axis. If it helps, you are more than welcome to create a little XY table and plug in 0, 1, and 2 and see what happens. So if I plug 2 to the 0 power, anything to the 0 power is 1. So 0, 1 is a point. If I plug in 1, 2 to the first power is 2. So 1, 2 is a point. And then 2 to the second power is 4. So 2, 4 is another point. 2, 1, 2, 3, 4. And then we connect to create our exponential curve. So this is doubling. We're doubling the value every time, which means that in the next one, we are going to triple the value every time. So if you wanted to create your little XY chart, do 0, 1, and 2, again, knowing that we're not going to go below this, anything to the 0 power is 1. And now we're going to triple them. So 3 to the first is 3. 1 times 3 is 3. And then if I plug in 2, 3 squared is 9, which means, again, 3 times 3 gets me to 9. So that's going to be way up here. So the larger the number here, the steeper this exponential graph is going to be. And the smaller it is, or the closer it is to 1, I should say, the less it's going to be. Next one, we want to graph 4/3 to the x power. So again, there's no shift in this. There's no added pieces, so we cannot cross that y-axis. So we can do those same points again, 0, 1, 2. 4/3 to the 0. Anything to the 0 power is 1. So now we're going to plug into the first power. 4/3 to the first power is 4/3. That's 1.3. So I'm up a little bit. All right, let's see. 4/3, if I square that, that's going to make 16 over 9. And that's about 1.8. So we're getting a little higher here. So it looks like this one's real narrow. It's not increasing very quickly here. As long as you have you need to have 2 points, and then the rest of the graph will go from there. I like to graph 3 just because sometimes it helps me see how steep that is. All right, next one, graph f of x equals 2 to the x minus 1. What this means is it's going to be the original 2 to the x graph, except that we have now shifted it the opposite of this, so 1 to the right. So 1 to the right. So I'm going to draw the original graph here in a light color. So 2 to the x, if you go back to the first one there, it was 1, 0, 1, 1, 2, and 2, 4. This was the original graph. Our new graph, everything is shifted 1 to the right. So now I'm going to be here, here, and here. So that's one way to do it. If you know how to graph the original one, we just shift everything to the right one place. Using that similar concept, instead of starting at 0, we're shifting 1 to the right. So we're going to do 1, 2, and 3. So 2 to the 1 minus 1 is 2 to the 0, which is 1. 2 to the 2 minus 1 is 2 to the first, which is 2. And 2 to the 3 minus 1 is 2 squared, or 4. So again, all those points should match. Okay, so now we're going to do another transformation on that 2 to the x graph. We are going to negative it and then add 2. So the first thing it does is it takes that original 2 to the x graph, and over this negative outside here is going to flip it over the y axis. And then after we do that, we're going to move it up 2. So I'm going to draw this in a few steps. So step 1 is the original graph. It was 0, 1, 1, 2, 2, 4. Original graph. Okay. Step 2 is flipping it over the y-axis. So flipping it over here means all my y's are going to change to negatives. So instead of 0, 1, I'm at 0, negative 1. Instead of 1, 2, I'm at 1, negative 2. And instead of 2, 4, that was 2, 4, it should be up there. I'm now at 2, negative 4. Again, I'm going to just dash it because this isn't my final answer. Now, the last thing I have to do is shift all those points up 2. So this point's going to go up 1, 2. This point's going to go up 1, 2. And this point's going to go up 1, 2. And this, now remembering the original line you did not cross was 0. This means the line we cannot cross, so let me put these colors here so you know, is 2. So I cannot cross this line on my exponential here. And purple is my final answer. Now, if you don't like working with the transformations, you very easily could create a little XY table and plug in 0, 1, and 2 and see how they work. Okay? But I'm going to do transformations again with this one over here. So we're going to work with our 3 to the x graph, which we did graph already. So that was 0, 1, and then 1 was at 3, 1, 2, 3, and then this one was way up at 9. So this graph is going to, let's see, x plus 1 means I'm going to move left 1, and then everything's going to move down 2. So let me see if I can get my 9 on here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll do that just so that I can then, this one I can do all in one step. Let's see here. Okay, so take every point, move it left 1 and down 2. So left 1, down 2. This point here, left 1, down 2. This point here, left 1, down 2. And we have to remember where that line is that we cannot cross. So we cannot cross that negative 2. So this guy can't cross that. And there's my graph. The last thing we're going to do is find the function from the graph. Now this is going to maybe be a little trickier. We'll be able to figure it out. So what I'm going to do here is I need to kind of figure out how much this graph is going up by, and I got to use those points. So I'm going to find the first point that goes over 1 and up 1. And that's here to here. That's over 1 and up 1. And what I need to do is determine how the next one changes. Over 1 and up 2. So I went from 1 to 2. That means we are multiplying by 2. The base is 2. 2 to the x. Now, if I follow that, the next one should be over 1 and up 4. And if I check over 1, 1, 2, 3, 4, yes, it actually is. Now, we need to think back to the original 2 to the x graph. So the original 2 to the x graph starts at that 0, 1 value. So this guy here should be up here at positive 1. And it's down here at negative 3. So this graph has been shifted down 3. So the function for this is 2 to the x and then a minus 3 on the outside. Here's our next one. This one is not shifted down at all. It's not shifted to the right or left. It's just where it is. So what I see here, I almost see this like the original ones we were doing at the beginning. I've got 2 points, 0, 3, and 1, 9. This is my initial value, A. And then from there, I can solve for B. So this is another way you could do this. So the initial value is A. So 3 times B to the x is what we're going to go for here. And let's see. 9 equals 3 times B to the first power. Well, that means 9 equals 3 times B. So if I divide everything by 3, 3 equals B. So final function, 3 times 3 to the x power. The way I knew this one was in this original form was because they give me that starting point and it does not go below the x-axis. Looking at this last one here, we can see that it is below the x-axis, so we know we have gone down 1. So we are holding here. We are not going any lower than negative 1. So I know whatever my function is, something to a power, we're going to have minus 1 on the end. And what I need to figure out is how much this is increasing by. How do we go from 0, 0 over to 2, 15? So I need to think to myself, if I plug this in, let's see, f of x, so 15 equals something squared minus 1. So I'm using this point here, the 215. 15 is the answer to something squared minus 1. So if I add 1 to both sides, 16 equals a squared. Okay, a is 4. So 4 to the x power minus 1 is my original function. We can double check if I plug in 0. 4 to the 0 is 1. 1 minus 1 is 0. So we got that 0.00. And double check, 4 squared is 16 minus 1 is 15.